Hi everyone, I'm Dr. Diana and welcome to Uncovering Earth. Today we're going to look at lava and why it might be of some interest to rockhounds and mineral collectors. Let's get started. These are some of the most well-known minerals and rocks associated with volcanoes and volcanic structures. Some of these are unique to certain types of volcanoes, but others are more common. Learning about different types of volcanoes may help you find some of these minerals, as well as gold, silver, copper, and opals. Let's cover some basics. Magma is molten rock. Magma, which cools underground, is called an intrusive rock. The magma stays under the surface of the earth and will cool in several different forms. Magma, which reaches the surface of the earth, has a name change, and it is called lava. Lava cools on the surface of the earth and can create several types of igneous rocks. People may often discuss intrusive or extrusive igneous rocks. Again, igneous refers to the molten nature of the rock, and it includes both magma and lava. When magma and lava are used, they describe whether the liquid is above or below the surface of the earth. We're looking at lava in this class. Magma moves through different layers of rock, and in the video on magma, I covered all of the different forms that you see with the numbers on it. In this class, we're looking at just number 6, and this is a conduit pipe to the surface of the earth, where the lava or the magma will spill out onto the surface of the earth. Again, when it reaches the surface, magma becomes lava. So there is a name change from magma to lava. So in this class, we're looking at the surface features of volcanoes. For this class, we are focusing on the lava that extrudes from volcanoes. In this diagram, we see a cross-section of the earth. The mantle is labeled as number 1. This is an area of liquid and semi-liquid rock, kind of like a slushy, where it's partially frozen and partially liquid. So the mantle is super hot. So it is liquid and then kind of chunky rocks. The mantle is in a constant state of motion and circulation, much like a pot boiling water. Number 2 represents the crust on the ocean floor. Oceanic crust is thinner, and when it meets a thicker continental crust, it will move underneath the continental crust in a process called subduction. This diagram shows oceanic crust subducting under continental crust. Number 3 represents the depth at which the oceanic crust starts to melt due to the heat rising from beneath it. The Earth has a lot of radioactive materials, and that's what keeps the magma in the mantle molten. So as the oceanic crust goes down into the mantle, it will melt. As the oceanic crust moves downward, it also takes with it seawater and the sediments that have been built up on top of the crust. This mixture of seawater, sediments, and magma create a unique kind of chemical soup. It can also have trapped gases such as oxygen and carbon dioxide mixed with it. Number 4 represents rising magma. So it's rising from down in the mantle to the surface of the earth. After the oceanic slab partially melts, some of the magma, that molten rock, will begin to rise towards the surface of the earth. It does this because of the water that was part of the melt. The hydrogen and oxygen that make up water become gases at high temperatures, causing the magma to rise. The magma comes out on the surface of the earth as lava. In this case, because we see the diagram that the magma is coming out on a continent, on land, that magma is going to have either an andesitic or rhyolitic type of lava. Number 5 represents a hotspot volcano. This is located in the middle of the ocean, And this one has a direct conduit or pipe leading right into the mantle. So because it's on an oceanic plate, it is going to exude a basalt lava. This is a cutaway diagram of a volcano. And you can see there are several different structures to it. This is an average type of volcano. They may be structurally a little bit different based on the type of materials that are coming out on the surface of the earth. So in this one, we see the magma chamber at the very bottom of the diagram, and it's connected to a conduit or pipe, number 3. And that pipe goes all the way to the top, and you can see as the pipe gets closer to the surface of the earth, it widens up into what is called a throat of the volcano. It just means it's a larger area for the lava to accumulate before it spills over and creates a lava flow. On the sides of the volcano, we see that, first of all, it's placed on top of what they're calling bedrock here, that really just means the surface of the earth. And then the base of the volcano is sitting on that surface of the earth. And there are alternating layers. We'll have layers of lava and then layers of ash. And then often you'll have another flow of lava on top of that ash. And many times these can alternate over either short or long periods of time. It really varies by volcano. Each volcano is going to have a different type of lava flow. So some of them will have more rapid flows, and some of them will be much slower and more explosive. You can also have little branching conduits like number 6 on the side. And so in that case, number 6 and number 5, it doesn't reach the surface of the volcano, but there's a conduit on that side where lava is accumulating. A little bit further up, we see in that area of 11, 12, and 13, what they call a parasitic cone. It just means an extra little cone on the side of the main volcano where the lava is going to flow out the sides of the volcano. Now, lava flowing out the sides of the volcano is very common. Matter of fact, after the volcano has stopped erupting, the lava will flow out of these little side tubes, and they'll create caves that a wide variety of wildlife as well as humans can explore. So this is kind of just an average diagram of a volcano. And I also want you to note the ash clouds. So volcanoes typically produce a lot of ash as well as poisonous gases. As I mentioned earlier, the chemical composition of the magma and eventually the lava is going to vary greatly from location to location. This is because that magma has to come up often through many layers of earth. And each location around the world has a unique composition of layers. Some areas may have a granite bedrock topped by many layers of a variety of sediment. Other areas may have more of a mafic bedrock, very dark rock, and have no sediment on top. So that magma coming up through those different layers is going to melt the layers, and that melt is going to add into the molten magma and change the chemical composition. Because of this, each volcano and each eruption has a unique chemical signature. So let's look at the types of magmas or lavas that are most common. So typically we look at the lavas as a percent of how much quartz or silica is present in the lava. So if you have the highest level of quartz or silica, then it is considered felsic. So this is going to have 66 to 76% silica. The rocks that come from this are typically very light in color. They'll be white and pink and shades of kind of peach color. They may have a few specks of dark minerals in them, but overall they're going to be very, very light in color. Then you're going to have an intermediate magma or lava. That's going to contain a little bit less silica, 52 to 66%. And this is going to have a mix of color. So typically it is going to be pretty even mixture of light crystals, light colored minerals, and dark minerals. There are a lot of feldspars that are both in the felsic and intermediate magmas, and they are very light in color. And then as we reduce the amount of silica, we come to the mafic magma. So this has 45 to 52% silica. It's got a lot of magnesium and iron, and a lot of really dark minerals are common in this. And then the last type of magma is called ultramafic magma. It has the lowest amount of silica at only 38 to 45%. This typically has a lot of olivine in it as a primary mineral. So I've already mentioned this, but the reason there are different types of magma is because of the rocks that the magma flows through to reach the surface of the earth. So we want to look at the type of rocks that are melted into the magma. So you have the base magma that occurs in the mantle, and that tends to be mafic in origin. It has a lower amount of quartz. But as it moves up towards the surface of the earth, it encounters other rocks that have higher levels of quartz. So the rock that melts to form the magma is called a source rock. And each type of rock, igneous, sedimentary, or metamorphic rock, contains a unique mix of elements and minerals. And when these melt into the magma, they'll create a brand new composition, and they'll become either felsic, intermediate, mafic, or ultramafic, eventually when that lava or magma cools. Another measure for lava is how viscous that the lava is. Viscosity measures how easy it is for lava to flow. The more viscous it is, the more difficult it is to flow. So think about like cold molasses. It doesn't flow well at all, even at room temperature. And then if you make it cold, it's very, very slow. So that would have a high viscosity. Water would have a low viscosity. It's very easy for that to flow. So when we look at lava, the different types of lava and the amount of silica can determine how well that it will flow. So the lava that has low amount of quartz or silica has less viscosity. So that would be our basalt type of lavas, and that flows very easily. We see this in the lava flowing from the Hawaiian volcanoes. It's always basalt, flows very easily into the ocean, and it's very smoothly flowing, almost like a stream or river. At the other end of the scale would be a rhyolitic or felsic lava, which is high in silica, high in quartz. That type of lava doesn't hardly flow at all. And as a matter of fact, it's far more explosive because it has more gases contained in it. So rhyolitic lava or felsic lava really doesn't flow. It just kind of chunks up in the crater of the volcano, and then it explodes. There are two types of textures for lava, and it's just a way to describe the look and the feel of the smoothness or roughness of lava. And both were named in Hawaii, so I may not get the pronunciation correct. So the first one is called Pahoehoe lava, and that is also called a smooth, ropey lava. So there are flow lines that are in the Pahoehoe lava, but it's very smooth. You can move your hand over it without getting cut or anything. The second type of lava, again, is this is for texture, is called a'a. And basically, it's the sound you make when you step on it, because this type of lava is very, very rough with very sharp edges, and your feet would definitely get cut up. I had a friend who was a park ranger at the volcano in Hawaii, And she said that they had to regularly get new work boots because the type of lava, the lava, would cut up the bottoms of the soles. So every few months, they would have to get new work boots to protect their feet. The types of textures we just talked about, pāhoehoe and lava, are commonly found in basalt. Another form that basalt can take is called pillow basalts. And this pillowing shape occurs underneath the water. So we see this again in Hawaii and around other island type volcanoes, where the lava will flow into the sea, and the interaction between seawater and the hot lava will create kind of a skin on the outside of the form, and it creates these kind of rounded balls that they call them pillows. So in this particular diagram, we see a graphic, a drawn graphic showing how a new pillow forms. In this case, the lava or magma is coming up from under the ground, but underneath the water, and then it's being squeezed out to form a new pillow. The lower right picture are pillow lavas that have been formed underwater. And on the left is on land. So this is a case where when we see these pillow lavas on land, we know that the sea level has dropped or the land has risen to expose these. So these are ancient or old pillow lavas. This little chart is kind of a summary of what we've been talking about. So it includes the amount of silica content near the top. At the bottom, it shows the viscosity. And then in the middle, it shows the temperature range. So if you look on the left-hand side under basalt, we can see that that is a low silica content, 48 to 52%. Probably still more than what most people might imagine, because when we look at basalt, it's a gray to black in color. And so we don't see that light colored silica as being super obvious. But it has a very high temperature. So basalt has a very high temperature, and this results in a low viscosity lava. Means it flows very smoothly, very similar to water, just a little bit slower than water, but it can flow like a stream. And, obviously you need to move it out of the way if it's coming towards you because it will flow relatively quickly. The basaltic volcanoes typically have a lower amount of poisonous gases that are released. They can still have some, but they're going to be lower than the opposite end of the spectrum, the rhyolitic volcanoes. And then as we move towards the right of the chart, you'll see that andesite is a little bit more of a mixture of more quartz, and then the lava is starting to become more viscous. It's becoming just a little bit harder to flow. And as you continue towards the right side till you get to the rhyolite, you can see that silica content really goes up. So around 75%, 68 to 77%. So 3/4 of the lava is silica. This results in having very light colored rocks when it actually cools. We also have a drop in temperature. So higher silica, lower temperature, high viscosity. So the rhyolite is the type that does not flow. It kind of chunks up in the neck of the volcano. And this is the type that's going to be explosive, and it's going to release a lot of poisonous gases. So when we look at a more intermediate level of silica content, we're going to be looking at the andesitic types of lavas. It's an extrusive rock, again, with kind of an intermediate level of silica content, and they always occur along subduction zones. These have a little bit lower temperature than basalts, and they flow a little bit more slowly. So andesitic lavas tend to be more of a gray color in composition. So basalt tends to be dark gray to black. Andesitic rocks tend to look more like a lighter gray. And then, of course, the rhyolite is typically pink to white in color. So the andesitic rocks and lavas are named after the Andes Mountains in South America. And in the graphic, you can see the western edge of South America is all along that is a subduction zone. So that part of the world has a lot of earthquakes and they have a lot of volcanoes. And the lava that comes out of those volcanoes is predominantly andesite. Let's look at rhyolitic lava now. So it is extrusive, just like the other lavas, and it is felsic in composition. That means it has the highest silica content. And it usually is always a light color. So it's going to be pink, pink with white, or white, and then it might have a few black minerals in it, a little bit of magnesium, but it's going to be dominantly very light in color. And the intrusive equivalent is granite, which is also pink to white in color. So when this type of lava is moving up through the conduit pipe of a volcano, it moves very, very slowly. It contains a lot of gases, and it doesn't really flow out of the volcano. It kind of creates this chunky texture at the top of the volcano. And then if there's enough buildup of gases, it will explode. These are the most dangerous types of volcanoes. And the most well-known of these types of volcanoes is Yellowstone. Yellowstone is the largest volcano on Earth, and it has had multiple major eruptions in historical times. It has not erupted since humans have been in North America that we know of. And the most recent one was around 600,000 years ago. So 300 to 600,000 years ago. So it does not erupt very frequently. But because it is such a large volcano, it is well monitored. So there are monitoring stations all around the Yellowstone caldera, and many, many scientists study that particular volcano. In this graphic, we're looking at a comparison of volcanoes based on the amount of erupted ash from different eruptions. The graphic is kind of divided into two parts. On the left side are the eruptions that had the largest amount of volcanic ash, and on the right are some of the smaller amounts of volcanic ash, but still quite large. So on the right-hand side, one of the more commonly known ones in North America is Mount St. Helens. It erupted in 1980, and it's located in Washington State in the United States. And this eruption was the most deadly and economically destructive event in U.S. history. But you'll note Mount St. Helens is represented by the second dot from the right-hand side. So the one on the furthest on the right was Mount Pinatubo from the Philippines in 1991. And that was the second largest volcanic eruption in the 20th century. So Mount St. Helens is significantly smaller. To the left of Mount St. Helens was actually the largest eruption in the 20th century, and that took place at Nova Rupta, Alaska in 1912. It released 30 times the volume of lava that Mount St. Helens released. So those are some of the smaller ones. The next two over were from the 1800s, and Krakatoa in Indonesia in 1883, and then Tambora in Indonesia in 1815. The Tambora eruption, which is the one on the left side of the 18th century group, is actually the most powerful volcanic eruption in recorded human history. Now, on the left-hand side, all of those really large eruptions, those happened prior to the advent of humans. So 3 out of the 4 are from Yellowstone. And then the fourth one is from the Long Valley caldera in California. And all of them are more than 600,000 years old. Matter of fact, the most recent one was from Yellowstone, 630,000 years ago. And the oldest one and the largest one that you see all the way on the left side was from 2.1 million years ago, and that was also at Yellowstone. So we see a wide range of eruptions. Now, more recently, Mount Etna in Italy has started spewing ash and gases, but no lava has emerged at this point in time. So a lot of volcanoes do this in that they'll have a lot of release of ash and gases, but no lava will come, and then they'll quiet down for years. And then again, it'll repeat with the ash and some gases. So eruptions can look very differently. Sometimes they include lava, and sometimes they don't. Another feature commonly found near or even on the side of volcanoes is geothermal vents. These vents can emit a wide range of things, everything from gases, a lot of times it's sulfuric type of gases, as well as a mix of other types of gases, or it can also emit water vapor and water. So what happens is there's natural groundwater that flows around a volcano. And as the lava or as the magma starts to rise to the surface, the ground gets heated and it heats this water. And this water, heated water, can start to vaporize and come out in vents. A vent could be a fissure along the side of a volcano or in the land surrounding the volcano, or it could be a feature like Old Faithful, where you have a kind of a set fissure and the water erupts along with steam. And again, this is due to rising magma in the conduit. Now, in the case of Yellowstone, there hasn't been an eruption in many years, but the magma body is close enough to the surface that it is heating up the groundwater that's in the area. And it also enables a lot of the minerals to dissolve more completely in the water, so that when the steam and when the gases come out of these vents, a lot of the vents are lined with minerals from these geothermal vents. So the minerals circulate in the water, and then they're released in vapor or steam, and they deposit on the side of the vent. So you can get some very unique deposits from this. There's a lot more to cover on volcanoes that I'm not going to be covering in this particular class. So let's go back to some of those minerals we saw at the beginning of this presentation. Let's go back to peridot, which is also known by geologists as olivine. It's the mineral olivine. So peridot is found in basalt lava flows and in volcanic bombs. So what is a volcanic bomb? As lava is rising up through that conduit pipe, ready to come out of the top of the volcano, some of it's going to be thrown into the air. As it's thrown into the air, that lava cools relatively rapidly, and it creates what's called a volcanic bomb. I found one in California, looks really similar to a football. You have the elongated shape, and it's slender, and as that is cooling, the peridot can be in the magma, in the lava that's coming out, and then it's encased in that volcanic bomb. Most commonly, peridot and olivine is found in the basalt lava and ultramafic lava. So ultramafic lava is dominantly olivine, so you're going to find a lot more in ultramafic. And you can find those in Arizona, Hawaii, and the Canary Islands. The next mineral that was mentioned was zircon. Zircon is used a little bit for gemstones, but it's used more frequently for radiometric dating. So this is the mineral that contains very, very low levels of uranium-238. And based on the radioactive decay of the uranium that is encased in the zircon, scientists can determine exactly how old that particular crystal is. So the oldest ones so far were found in Jack Hills in Western Australia, and it was dated back to 4.4 billion years old. Again, basically they measure the amount of uranium that is remaining and determine the age from that. You can also find zircon in really several places around the world. It's found in both extrusive and intrusive felsic rocks. So these are the rocks with the high silica content. It's going to be rhyolite and granites. You can find gem quality ones in Montana, Virginia, and the Appalachian region in the granite batholiths. Sri Lanka is the primary source for gem quality zircon, and those are often made into faceted stones and used in jewelry. The next one is known by rock hounds as bumblebee jasper, but this is a misnomer because jasper is quartz, and this particular type of rock has no quartz at all in it. The correct name for this is sulfuric travertine. So travertine is a calcium carbonate material that originated as limestone, and you have some additional minerals added to it. And this particular type of rock is only found in Western Java. And it was really recently discovered in the early 1990s. It's kind of near a volcano, but it's not at the volcano. So it's really in areas where there's a lot of geothermal vents. And I would imagine that maybe there's a layer of limestone underneath. There's not a lot of information online as far as the type of geology that surrounds this area. This is notable to watch for because it is quite stunning to look at. The colors are just wonderfully vibrant. But this is a rock you have to be really careful of. First of all, it contains a lot of sulfur, and a lot of people are allergic to sulfur, high quantities of sulfur, and they may get an allergic reaction from it. But more importantly is it contains arsenic. Arsenic is a hazardous material, so this is definitely a rock that you need to wash your hands very well, and I certainly would not wear it directly against the skin. So if it's incorporated into jewelry, it needs to have a metal backing so that it does not touch the skin directly, and wash your hands after handling it. Obsidian is a felsic, naturally occurring volcanic glass. So this means that it's very high in silica, around 69 to 77%. And the other elements like iron and magnesium are very, very low in composition. This rock is dominantly extrusive, meaning it comes out of a volcano, and frequently it can have a flow pattern. Much like lava, it will flow, but it cools so rapidly that crystals don't have time to form, and it turns into glass. So again, it's felsic, so that means that it's a rhyolitic type of lava event that obsidian occurs with. The unique feature to note about obsidian is the way it breaks, or its fracturing. It breaks in a conchoidal form, very similar to how glass breaks. So if you break a window glass, you'll see on the edges of the break, there are these curved shapes. Those are called conchoidal fractures. In this particular photo, you can see those in the photo of the arrowhead, that highlighted area in the center of the photo. You can see the curved shapes of where the breaks, where that had been napped off to make the arrowhead, and it broke with those curved shapes. That is called conchoidal fracturing. Diamonds are a little bit different than the other rocks and minerals that we've been talking about because they kind of are deposited in kind of a two-step process. So diamonds naturally occurring form very, very deep within the mantle of the earth, somewhere between 56 miles to as much as 400 miles underneath the surface of the earth. And they don't form instantaneously, the way some crystals can actually form, maybe not instantaneously, but in a short time period. Diamonds take a long, long, long time to form, millions to even billions of years. It's estimated that the majority of diamonds and the majority of volcano pipes where they come from, the old ancient volcanoes, are at least 1 billion years old. So if you have a naturally formed diamond, it is most likely at least 1 billion years old. So after they're formed down in deep inside the mantle, then the circulation occurred where that magma that held these diamonds began to move towards the surface of the earth. And they came up to the surface of the earth in conduits or pipes that are called kimberlite or lamproite pipes. And these volcanoes that carried these specific rock types are only found on the core or the cratons of the continents. They're not found in more modern volcanoes. So the volcanoes themselves are also very, very ancient. These types of volcanoes produce diamonds in only certain areas of the world. So for instance, in Africa, northern Russia, Western Australia, there's only one location in the United States in Arkansas, and then also in the Canadian Northwest Territories. Other minerals are also associated with volcanoes, and many of these come from the hydrothermal waters that flow through fractures and that cause the steam vents and geysers that appear near many volcanoes. So the water will flow around naturally. It's just groundwater that flows, underneath the surface of the earth. And when a volcano is erupting, or even the magma is just moving up and down in the pipe with no eruption at all, that hot magma actually heats up the water that's underground. And what happens is a lot of minerals can start to dissolve. So for instance, quartz dissolves at a very low temperature. And sometimes elements such as gold, silver, and copper can be carried in very tiny quantities in these waters. Well, these waters will move through the different fractures that start to appear as the magma moves up and down in the pipe. So volcanoes typically have many, many, many earthquakes prior to eruption, and those earthquakes create these tiny fractures throughout the entire region. Well, this hydrothermal water, this water that's been heated up from the magma, will flow through these fractures, and many of those dissolved elements like gold, silver, and copper will start to attach to the walls of the rock. And then as that water cools, other minerals like quartz will also attach. So typically, if you're looking for gold, silver, and copper, you will look for these veins that are in these fractures, and you want to look for the ones that do have a lot of quartz in them, because oftentimes the metals, the gold, silver, and copper, will also be present. Now, opals are also listed too, and opals tend to form with more water. So they're going to be closer to areas that have the different vents where it's actually venting the hydrothermal water, and not necessarily along fractures, but more closer to the surface where the water might come out, for instance, around geysers in areas like that. So that was just a very brief introduction to volcanoes and some of the minerals that you might find around or near volcanic structures. Believe me, there's huge volumes of additional information on volcanoes and volcanology. So you may want to continue looking and learning more about volcanoes and the types of products that come from them. But this is just a little map showing the currently active volcanoes in the world. So currently active means they've erupted within recent recorded history in the last 100 years or so. And you can see that volcanoes are distributed very widely over the earth. They are dominantly found near subduction zones, but you also have volcanoes that are located in other areas too. So if you're looking to do some mineral prospecting, it's likely that you might have a volcano close by, or you could take a really fun trip to some place that does have one. I'm located in North America, just on the north side of the Gulf of Mexico. So we're just zooming in a little bit to see what kind of volcanoes are in North America and in Central America. And you can see the vast majority of them are on the west coast. They're near the Pacific Ocean. The Atlantic Ocean side doesn't have a lot unless you look down into the Caribbean Sea area. So we have quite a few on the eastern Caribbean Sea, and then all the rest are dominantly on the west coast. And again, these are active volcanoes. So I'm located in southern Alabama at the northernmost point of the Gulf of Mexico. And we want to look at where are the closest volcanoes to us, or volcanic structures even. Can we go looking for old ancient volcanoes that may have been nearby? So what are the guesses? Well, as I mentioned, the eastern part of the Caribbean has a number of active volcanoes. And Mexico also has active volcanoes. And then we know the Pacific Northwest and West Coast of North America has many active volcanoes. So which one is closest? So my guess originally was either the Caribbean or Mexico. So when I did a little bit more investigation, I was really surprised by the answer. The answer was Jackson, Mississippi. Turns out that millions and millions of years ago, there was kind of a rift that formed about 400 million years ago. It's also associated with the New Madrid Fault. And there were a line of volcanoes on both the western and eastern sides of this faulting area. And some of those ancient volcanoes, although they're buried with huge amounts of sediment, half mile or more buried underground. But these volcanoes, these ancient volcanoes, are still having magma go up and down the conduit pipes. Well, the closest one to my area is actually Jackson, Mississippi. So this particular volcano has not erupted for approximately 66 to 75 million years. So it is considered dormant, but the magma still occasionally goes up and down the pipe. And we know this because it was found when they were drilling for oil. And they were going down to depths that really weren't that deep, yet the groundwater was hot. Well, what was heating the groundwater? So if you go down deep enough, of course, yes, the water and any fluids that are deep underground are going to be hot because you're approaching the mantle. But closer to the surface of the earth, there isn't normally anything that heats the water. And they were finding water that was over 100 degrees in temperature. So, the question was, what is it? What is causing this heating process? And upon further investigation, they found that there was this volcanic pipe, this conduit, that still had magma that moved through it. This movement of the magma also solved the mystery of why so many buildings in Jackson, Mississippi have foundation problems. Because when magma moves up and down the pipe, it's not just moving up and down in this relatively small, narrow area. It's causing uplift for miles around the pipe. So the entire ground around the pipe also lifts upward. And so this uplift and then the release of the uplift, which causes a sinking, continually occurring over many, many years, may only occur once or twice a year, but it's moving more than what a foundation should be moving. And so it causes problems in the foundations of buildings that are built on top of it. This particular ancient volcano also contains the largest deposit of carbon dioxide in the United States. So, surprise, there are buried volcanoes. Could there be a buried volcano near you? While Jackson, Mississippi has a buried volcano, the closest volcanoes that we can see above ground to the northern Gulf of Mexico and southern Alabama are located in the Caribbean and in Mexico. There are many volcanoes in this area, so the Eastern Caribbean has quite a string of volcanoes. And throughout Mexico, central and western Mexico, there are many active volcanoes in that area. So if you want to go hunting for unique minerals and rocks that come from volcanoes, you may consider visiting those locations or head out further west to the western coast of the United States and Canada. Thank you for tuning in to Uncovering Earth. The slides following this show all of the references for the photographs used in this presentation. I hope you enjoyed this. I hope you'll come back soon and see some of our other presentations.